The first one is the learning understanding from queries. There are two main functions it supports: instantaneous query and graphing with time series. The right side just shows a very simple example. So just imagine, right, currently there are some abnormal traffic pattern was detected, and all the analysts on call get this alert. What they're going to do, they really want to find out which segment really contributed to this kind of abnormal traffic pattern. In this small example here, I just show a very, very simple query that segment out abnormal spike for sign up from specific IP country code. With this, our analysts could really dive into suspicious segment and sample those users and looking into their similarity of the user, finding signals that can somehow help them to determine whether this set of users is good and bad. So once a decision made, they could separate out the traffic and sizing the impact and exploring signals, and hopefully if something really bad, they really want to operate them as soon as possible. So that leads to the second function Guardian provides to our stakeholder, which is to allow they translate their learning into simple Guardian rules. So I just show a very easy understand example. By the way, this is a fake example because in the real world it's much more complicated than this one. One of the surveillance technique, the bad behavior they would like to do is social engineering. So for social engineering, they usually want to touch base with you. They want to say good words to you, but their ultimate purpose is get this conversation of Pinterest platform. What they really would like to do is they will start with messages sent, trying to get connection with you, and hopefully you can respond back, and they can. So we have a lot of rules to detect this kind of social engineering in the platform. So our analysts will write this kind of rule in this system and segment out the set of user who is doing these things. Once they confirm this set of users are really bad, so that can really action immediately by launching a Guardian rule in the in the below. Just translate, replace the select keyword with an action with a UDF of operation they want to do, and make the all the conditions living there. Once they launch this type of rule, our internal system can get really processing this kind of information and take the action immediately once they get this message. So this is the rule functionality. So another important feature Guardian provides is to backfill the action. So there is some time between we detect this harm and when the harm really started happen. In certain cases, we detect much later than the event, like the harm events happening. In those scenarios, we really want to switch the platform, like get all the bad users out in one click shot. So this feature supporting this, we call it rewind operation internally, but that literally is supporting a rule action backfill. Last but not least, Guardian has a very unique UDF internally which can help creating trend analysis. Like here is a simple monitor rule look like. So once this kind of monitor rule activated, stats data will be generated and consumed by internal stats board system. Normally, alerts could be set up based on these trends, and there are hundreds of charts available today in Guardian for anomaly detection and obviously rule monitoring. All right, so we talk about the brief major functionality in Guardian. So at this point, I really want to mention a little bit about the current state of the system. The first version of Guardian was productionized in 2018, and it's built in with LISA and Beam technology. And as Pinterest grows, currently we are facing scaling and reliability issue with Guardian V1. particularly I want to highlight two areas. One is the query component. We are experiencing some issues like slow query, broken query, etc. In the rule component, we also noticed that there are increase of data index failure, which leads to enforcement action missed. So I think the fundamental root cause for the Guardian V1 is it actually applies a single monolithic architecture, just one for all architecture to solve query problems, solve data persistence problem in one single construct, which obviously is not going to work as we continue to grow. So here are a set of problems that we will need to solve in the next generation of Guardian. First of all, we will really want to maintain the operational efficiency aspect. That means we would really want to keep our user transparent during this upgrade. They can continue write the rule. They can still do a very quick turnaround time between the issue detection and enforcement launches. Secondly, we would like to improve the system's reliability by focusing on data integrity and enhance the streaming data pipeline delivery. Last but not least, we'd like to scale our Guardian in 3 directions. First one, make it scale out with the growing Pinterest traffic, which covers hundreds of events, billions of rows, and thousands of columns. We also want to make it scale out to handle hundreds to thousands of rules. Last but not least, we want to add more and more engineer support in the next generation. The goal, actually the vision we are seeing is going forward, we hope all engineers, they are all empowered and feel confident to contribute to the system and its feature development. So what is our tech strategy behind it? So we would like to adopt open source technology. And we want to transition from an in-house technical staff, which is only understood by a few people, to a platform that's powered by open source technology. These are a few open source technology we adopted for the Guardian V2 system, including Kafka, Flink, Starrocks, and Iceberg. All right, so now let's get into the third agenda of today. How are we going to do that? Here shows an overview of the end-to-end data pipeline that goes in and out of Guardian. As you can see in this architecture diagram, all events go through a data-enriched services, where all the event features will be fully hydrated. The feature enrichment process does many data fetching as well as computation to ensure that after the feature enrichment, the enriched event will be sent to Guardian core module, where both query engine and rule engine can access it. The query engine is powered by Starrock tables that accept real-time events. This allows all stakeholders to look at patterns and trends effectively once an anomaly is detected. And the rule engine could be performed on Kafka event stream as well as Iceberg tables through Flink SQL jobs. Okay, when the rule engine finds a rule hit, an action for the content or user will be initiated and sent to an action Kafka topic. Eventually, bad user or unsafe content will be taken off the platform. So now from here, I'm going to hand over the talk to Heng to dive into the Flink details.
Thanks, Sharon. I think everybody sort of understand the problem we're trying to solve. It's the critical systems, like Sharon mentions, protect the Pinterest, protect the pinners from different attacks from spams. We are re-architecting a platform using all the open source technologies we support at Pinterest, and we believe we've adopted the right architecture to address all those issues in those monolithic architectures. So let's look at how we use Flink SQL to solve different data processing problems. So basically, we use Flink SQL to do various data processing, and we have three types of Flink SQL jobs. The first type is we have some Flink SQL jobs, basically solving the problem, basically scaling down the problem with effective stream splitting and pruning. Let's look at that in more details. So as you can see, we have a data enrichment service, basically enrich the raw event and generate the enriched event, which is one big topic, contains billions of events and go to a topic. What we do here is we adopt a multi-level pre-processing Flink SQL jobs to kind of process and split and pruning those raw events. We have the first layer of Flink SQL job read that one big topic and generate multiple smaller topic. Basically, we group correlated event to a specific topic. For example, we have a topic for user-related events. We have another topic for ping-related events, and etc. Before everything goes into one big topic, now we have smaller topics. And these smaller topics are indexed into the star rocks to support fast analytics. We also have a second layer of Flink SQL jobs. Basically, read, for example, the ping event topic and split the data by event types. We have a ping create, ping reping, ping click through, and so on. So we have generated a more smaller, and we also have more topics, smaller topics generated from the second Flink SQL jobs. So why we're doing this? Basically, we kind of basically we want to have this centralized pre-processing steps done once, so that the downstream, no matter you are doing analytics, no matter you are doing actions or backfills, you don't need to repeat this data processing, filtering, and splitting in later stage. We want to do that once in the pre-processing stage, pre-processing steps, and this brings a lot of benefit. So on one hand, it reduces the scale of columns. As we do pruning, we just eliminate the empty columns. We reduce the number of columns from tens of thousands to a few thousand columns. On the other hand, we can also allow the downstream job to just process the data it needs to process, instead of reading everything and then apply filtering and a lot of data shuffle and data movement. By this, I think centralized pre-processing, we just, I guess, easily make the downstream jobs much more scalable. Before you need to process probably like hundreds of billions of events every day. Now, each smaller job just need to process at a much smaller scale, process the event at a much smaller scale, and we can easily handle 10x scale traffic. This is kind of validated through load testing. Then let's look at the second type of Flink SQL jobs. So we have a Flink SQL job basically produce a reliable data set with real-time data ingestion. So as you can see still in this graph, many times the data in Kafka is not, I guess, enough to support different type of use cases. For example, sometimes we need to kind of process historical data, like maybe 30 days or even before 30 days. But we cannot store data in Kafka for that long period. Data in Kafka has a few problems. Usually at Pinterest we have very short retentions because long retention means more infra cost. And also the data in Kafka raw data usually serialized in bytes, so it's not good for analytics. Also, when data in Kafka, it means the consumers need to usually read the data. There will incur cross AZ cross-region traffic. That will be like another cost. I think we're trying to minimize. So to solve these problems, we have these data ingestion jobs. Basically, read the data from Kafka and write to iceberg tables. This will easily solve all those issues I mentioned earlier. At Pinterest, we kind of build a real-time data ingestion frameworks. It's not only for the specific use case we talk about here, but It's a general data ingestion service. We read from PubSub topic. We are able to read from Kafka and also some other internal PubSub services. And it's Flink SQL, Flink table API jobs, read those data and write it to Iceberg tables. It continuously generates a new Iceberg table snapshot every few minutes when Flink checkpoint. And this checkpoint interval is configurable, and we can easily kind of reduce this maybe to less than 1 minute if we kind of really want that low latency. With data in Iceberg, we are able to kind of easily support processing the historical data. We can also support big data analytics, and especially we can unlock the near real-time data analytics. Think about the end-to-end process. We have real-time data enrichment from the very raw event. We generate an enriched event. We have Flink-based pre-processing jobs, and then we have Flink-based data ingestion jobs. The end-to-end latency can be controlled at the minutes level, and basically it means once the data is in Iceberg, committed as a new snapshot in Iceberg, the downstream can read the data. So the downstream can basically can access the online changes just in a few minutes, which is not, I guess, possible before we introduce these real-time data ingestion frameworks. So the third type of Flink SQL job is basically support different type of action rule. I will leave this to Sharon to share some examples.
Yeah, thanks. All right, so to this point, you may ask, how exactly a Flink SQL job could empower the rule engine? And really, this is leads us to the Flink SQL job, which is actually an action rule job. To begin with, an action rule, what is an action rule? Action rule is essentially a type of data manipulation language that selects a qualified data from a source and inject it into a sink. So an action in Guardian's world is a special type of message with the script format that could be understood by many internal systems. So the right example just shows a simple action rule. What this rule is trying to do is actually produce and deactivation script message to downstream services for execution. Once it finds the patterns, right? It is actually expecting the downstream system who is listening on this message to really operate on user who are involved into this event. The Flink SQL for action, if we can look into the problem closely, every action rule is backed by a Flink SQL rule. And the Flink SQL rule looks like this select template just in the slide, which is pretty simple. Includes a select keywords, rule name, rule version, UDF action, and a front keyword to the source table with a where clause condition. So to match this template to the previous example, the source table should be filled in with the message source table in the previous example. So the Flink SQL job for action DML execution, as we mentioned before, the Flink SQL rule job essentially connects to the sink with the action messages. So the full Flink SQL DML to be executed on the job is just insert into keyword with the sink. All the select statement could remain the same. In the world of Guardian, Kafka action is the sink of all the Flink SQL rule job, and the cluster of consumer, which is a cluster of services that listening on different execution, including cluster for rule review, cluster for the activations, software ban. So that's it. Wraps up the simple Flink SQL rule job. Now the next question is, how do we scale this rule for supporting Pinterest business needs? So there are 3 ways we are approaching this. So from the use case perspective, we provide the action as a UDF interface to expand our business operation. So in the scenario of event-driven business logic execution, all executable business logic could be wrapped into a consumer job. Then the Flink SQL rule could be created to trigger the action UDF. So in the case of new action, the app developer just needs to implement a new UDF function that passes down the essential parameters from the event to the business logic execution units. So in another word, the system integration problem has been transformed into a simple message communication problem in the Guardian setup. So from operation perspective, we developed a Guardian Flink SQL rule deployment system that could handle rule addition, removal, and update automatically. So it actually ensures rule activation could be done with a few minutes delay, and it significantly reduces operational overhead for all our users. So from job maintenance perspective, all jobs are run on stability string that's already optimized for throughput and latency. All the job capacity and resources utilization is actually being monitored and tuned when we see a room for improve. So this allows us to grow with Pinterest the traffic scales. All right, while closing out this presentation, there's still one more thing I really want to highlight for Guardian ecosystem, which is also a key part that makes all our stakeholders efficient. That is GSQL interface. As you can see in our architecture diagram, GSQL is the unified interface. All the things we do are actually behind the scene. All our user, stakeholder, their interface is the GSQL. From a user perspective, they only know about that, and they use GSQL to interact with the query and rules. Behind the scene, a lightweight GSQL translator will perform the translation for both rules and query for the backend software could execute. So for instance, it will translate the GSQL into a star raw query for analytics and translate GSQL into Flink SQL statement for data processing. How do we achieve this? So I really want to thank to the simplicity of GSQL spec. In the GSQL spec, we only expose one DML, which is the actions. So Guardian also deal with very simple data types, primitive type and list of primitive type. I want to emphasize that this is by design, and thanks to the ALT work done by the feature enrichment processes, we push all the data-heavy signal engineering into the left of this architecture. So this actually allows us to manipulate easy language, easy schema in the rule engine. While we're upgrading GSQL into its V2 spec, we also made adjustments to the spec to align with ANSI SQL. So all these design decisions here powers a very lightweight translator that could connect everything in this ecosystem. Last but not least, Guardian includes a lot of good work for an engineer, incorporating a lot of feedback from stakeholders and engineer leaders. We'd like to thank everyone for this work, and if you are interested in how this signal engineering being done, how we make Guardian simple with the shift left metadata population, I would encourage you to join tomorrow's session. We do have a talk related to signal engineering powered by Flink and Flink SQL. That wraps up our presentation. Now I'm going to open up Q&A.
Thank you for your talk. Really great. I'm interested in one fact. If I understood correctly, right, you're running one action as one Flink SQL job, right? So when I in a lot of cases there is a lot of actions, a lot of rules to execute, right? I had this, for example, in a telco where we had hundreds of rules to be executed. It would be super inefficient to run those hundreds of rules as each of them as a separate Flink SQL query, each of them pulling the data out of Kafka, each of them syncing to Kafka, etc., etc. That would be very resource inefficient. Do you encounter this problem as well? And do you have a solution?
So we are not actually during our production launches we do traffic testing. So we actually one Flink SQL job handles at least 20 rules. So we do not see any resource capacity on that area during our demo testing. So to answer your question directly, no. A Flink SQL job definitely handles more than one rules, and we are still just testing that out. And I can tell you for sure, it's definitely working for at least 30 rule, 100 statements.
I'm sorry if I misunderstood that, but
Yeah.
great, thank you.
Maybe just to add a little bit. So we have this so-called a job that is a bundle job that can support multiple SQL queries. So like Flink has an interface called statement stats, right? So you just add all those different Flink SQLs in that statement set and execute once. And the Flink runtime will just figure out the best job graph to execute those Flink SQL queries.
Hi, thank you again. How do you handle the Flink SQL updates that you have to do? So, for example, if you need to deploy a new version of your Flink jobs, let's say you make some modifications and then it has to now, because the existing job will kill it right away, and then how exactly do you handle the upgrades and stuff?
So internally, we have a job management system that keeps track of the rule and job deployments. That's where we handle the state of the job. So, does that answer your question?
When you do a job, it's difficult to handle, like let's say restarts or scaling for that matter, and also, for example, hopefully doing a job version, you have to have some technical things in sequence or stuff like this. And how do you handle that when there is a change?
Well, yeah, I think those are very common operations we see every day. Like you have a new version, you add a new rule. For example, you add some new columns, you update the table schema. You need to, anytime all these changes happens, we need to redeploy the jobs. And before we kind of redeploy jobs, we kind of have a CI/CD process. At the first deploy to staging, test, to make sure nothing breaks, and then we automatically deploy the production jobs. That's how we do that. We kind of automate all these steps so that there will be like a minimum human effort involved to kind of do this type of upgrade.
Let's say your engine already has some months in the pipeline on your instance, so when your job, when you do an upgrade on the existing commands, you clean them up. So, for example, you flush them out, or how do you handle this process? Because the events still need to be processed.
Oh yeah, I think we have to. Okay, so in our settings, we make sure at one time there's only one job that is running. So in case we need to do this type of upgrade, redeployment, we have to queue the current jobs. Before that, we get a save point or checkpoint, and then we redeploy the production job. So there will be a short time window where no job is running. We are not processing any events, but usually this window is kind of on the small, like a minutes level. There will be a small time when we don't have anything processing events. But I think this is tolerable in our settings.
Thank you. And you're welcome.
And Does your engine supports also UDFs and maybe match recognized clauses, which I find could be useful for finding patterns which are suspicious? Do you support that in your engine as well?
Yes, UDF is a very powerful interface we are supporting currently. We are working with Hans team to open up the Flink UDF, and also we are working with another analytical team to open up the Starrock UDF. So in the system, it actually talking to the two software pipeline to ensure the UDF functionality.
Because the same UDF will need to run in Flink as well as on Starrock.
Exactly, and we are purposely designing their CI/CD pipeline to ensure update and addition are following on the same track. So.
I think here maybe trying to clarify a little bit. So as we kind of show in some of the slides, like we have multiple SQL engines to support, like the Starrocks from SQL, right? Unfortunately, they are SQL, but they are not the same. So their UDF interface is different. So one of the challenges here is we want to have this consistent experience from analytics to action, but they have different APIs, they have different interface. So it's really hard to make sure we write a UDF that can run at two different query engines. So this is turn out like we have to write basically two UDFs so that the UDF can run in Starrocks, the UDF can run in Flink. But here we are kind of duplicate the logic, right? So it's kind of error prone. So we have to kind of figure out ways to make sure we have this consistent logic across different query engines. So this is one of the, I guess, the challenges with this.
Okay. This is an active topic with all the cross-functional partner team. We are actually trying to build a regression detection pipeline to ensure like any UDF updates, we need to ensure they are not impacting production. So we are enforcing user or the especially feature engineer, they want to use new UDF or try new things, they need to go through this pipeline and ensuring the CI/CD could run the regression testing to all existing production rules. So very hot topic currently we are working on.
Thank you for your presentation. Obviously a lot of cool implementations using these open source technologies, but if you were to estimate how much is like Pinterest internal extra config and extra development, like these UDF interpretations, part of the solution? Because obviously there's a lot of work that you've done internally to make this all work together.
I can give you estimate. For the CI/CD, it's actually all platform already have they already have some foundation on each cross-platform. So to fit our business need, we just need to ensure setting up the staging environment on their platform and run their existing infra to do the regression check, all these things. So based on this current already work there, so we need to add 1 or 2 months to build our things on top of that infra to ensure that. So yeah, something to just highlight is the schedule in the next 3 months for us to deliver that.
Any other question? Well, thanks, Ron and Hey. Amazing presentation. As usual, if you find this session useful, at the end of the day, you'll probably receive a link. It will really be interesting to hear your feedback so we can improve year over year and continue to have amazing content.